Okay, so the last talk of the day is from Rachel Lin. She'll be talking about a unified framework for succinct garbling via HSS. Go ahead, Rachel.
Okay, thank you. Thanks for the organizers for inviting me, and then thanks to David and then Xiao for giving all the wonderful introduction to Garbling circuits, which makes my job a lot easier. So this talk, slides are made together with my student Hanjun Li, and he is in the audience. Okay, so garbling circuits, typically that we think about the garbling Boolean circuits, but in my talk, but as you have heard, there are many different modes of circuits that we can think about. Typically that we think about converting it into a garbling circuit with two labels. And when you want to evaluate, the evaluator will get one of the two labels according to the input bit that is being evaluated. And today that the requirement is that given the label, one will be able to evaluate to get the output, and the security is that only the output is revealed and nothing else beyond about the input. And today we're going to think about the fact that the circuit itself is public. Okay? And because the circuit is public, the evaluator and the simulator both receive the circuit, and therefore we can actually hope for the garbling circuit to be much smaller than the circuit itself. Okay, so a very, very nice generalization is the arithmetic garbling circuit introduced by Applebaum, Ishai, and Kushlevitz in 2011. And they generalize garbling to evaluating arithmetic circuits. This won't be the focus of our talk today. However, one particular very useful mental model is to move away from thinking about each input wire has two labels. Instead, think about the encoding of the wire value as being the output of an affine function. Okay, so the garbler is actually going to output these affine functions for encoding the input. Each affine function itself is defined by two keys, which is basically its coefficient, AI and BI. And the label is going to be the evaluation of this affine function. And this is a strict generalization of the Boolean case because the choose one out of the two label is an operation that can be rewritten as an affine function with this A value and this B value. And when we move to this mode, we'll see that it actually opens a lot of different possibilities. In particular, as we see repeatedly this useful feature of free XOR, that the A value multiplied with the wire value is a fixed global offset. Okay? So garbling circuits needs no introduction. There's a lot of really interesting applications out there. And one personal feature that one personal thing that I really like about garbling circuit is it generates great theory and practice both. And we don't usually see such a cryptographic primitive. And in particular, one obsession that we have about garbling circuits is how large it has to be. And this is for good reason, because for any application of garbling circuit, we'll have to communicate this garbling circuit. So typically, we think about 2PC. This translates to, say, communication matters in an interactive protocol. But if you really think about it, garbling circuits is actually a non-interactive primitive. You send it once, right? Because it is non-interactive, optimizing for the size is particularly important because there may be scenarios where saving in size is multiplied by how many recipients there are for receiving this garbling circuit through, say, a broadcast channel. For example, I could publish a garbling circuit on the blockchain where space is really the prime estate. All right, so I'm not going to talk about garbling circuit without talking about the famous 2015 talk by Mike Ruslik about the practical garbling circuit advance 10 years ago. And in this slide that Mike was talking about on how large the garbling circuits are becoming, how smaller and smaller they are, measured in terms of rates. And the rates is basically how many bits you have to send per gate. In South Talk, we're now at 1 bit per gate. And generally, it's basically the size of the garbling material divided by number of gates. And a celebrated story in the past decades or so, or beyond past decades, maybe 2 decades, is that we can actually make the rate smaller than lambda. If you see in this slide, it is already smaller than lambda thanks to free XOR, right? And so if we look at the gobble circuit research, for a while it really looks like this. There's this gigantic literature on optimizing gobble circuit using symmetric key cryptography. Then there's itty-bitty of theoretical work about doing fully succinct gobbling using lattices and I/O, which can get gobbling where the size is completely independent of the circuit size. It only goes with the input and output size. This is asymptotically optimal. Except that this seems to be really two extremes, because on this hand, we know that using symmetric crypto, this is extremely fast, right? To compute, to gobble and evaluate, each gate corresponds to a constant number of AES calls or random oracle calls. On this hand side, it's really like, evaluating FHE inside AB. Okay, so, and I'm being polite by saying fast and slow. Really, it's like extremely fast versus extremely slow. It's kind of strange that why we only have these two endpoints, whereas it's really kind of like empty in the middle. And it's weird that why do we constrain ourselves to those two extreme points of design space instead of thinking about what about a broader design space? More generally, what can public key cryptography bring to gobbling? Okay, since we've already demonstrated a very, very big advantage using public key crypto, which is fully succinctness, a very nice angle to cut into it is understanding succinctness itself. Had a question?
Just naively combine the two by looking at subcircuits, like large subcircuit of the circuit, and do your fancy public key thing to this thing?
Possibly, nobody has done so. Yeah, because they are very siloed. There are two different sets of researchers. And that's why we are here today, which is to shake hands. All right, so since that we already see succinctness can benefit from using public key cryptography, so let's understand the succinctness. And instead of thinking all the way to the extreme succinctness, let's think about succinctness from scratch, where a minimalistic requirement of succinctness is the gobbled material is simply smaller than circuit description. And circuit description is actually number of gates times log of number of gates. And there's a huge space in between, which is basically partially succinct. You can go like close to one end to the other. And we can ask theoretically relevant questions, such as what assumptions enable what level of succinctness. We can ask practice-oriented questions. Can I have efficient succinct gobbling, fully succinct or partially succinct or minimalistically succinct? And I have not even touched on any of those fancier properties of gobble circuits, which would not be the focus of today. So I'm happy to report that there has been some recent advances, but this is really only the beginning of some much bigger research. What we can do now is we can have partially succinct gobble circuit with the gobbling is 1 bit per gate plus some low order terms, and using assumptions groups, which was not used before in gobbling. And the tools that are used here are linearly homomorphic encryption and homomorphic secret sharing techniques. So they're relatively lightweight. If you think about efficiency, as we have seen in Xiao's talk, which we won't go into too much, roughly if we instantiate using lattices and optimize it a lot, per gate it's about doing some constant number of ring multiplication and rounding. So each ring multiplication and rounding could be at the scale of several microseconds. That's what Xiao reported. If you use groups, of course, it's not going to be as efficient as lattices, but groups typically has benefit in getting concretely small gobble circuit. Okay, so I would say that in terms of efficiency, it's neither fast or slow, but let's say optimistic. And also we want to say that fast versus slow is in the eye of applications. Most of the deployed cryptography are actually at the level of milliseconds or microseconds per operation. So if we find the right application, this kind of technique can be useful.
Rachel?
Yeah.
Where's the security parameter? Maybe you're about to answer my question, but where's the security parameter in the middle?
So this low order term will have some security parameter inside.
I see. So it's like little OC times security parameter.
It will actually, in our application, with the right assumption, it's poly lambda.
Okay.
Yeah. Okay, so at a very high level, let's think about non-succinct as rate lambda, partially succinct as rate 1, and fully succinct as rate 0. Okay, so and let's not have this debate now, Yuval. So I'll give a little bit more history. Okay, so this is where before the recent works, we have Gabble circuit with rate lambda, and we have this like heavy machinery which give us rate 0. And like in 2023, that we had a result about Garbling arithmetic circuits, and there we first achieved the rate constant for very large modulus. Okay? But this gives us a signal that using public key cryptography, we can actually possibly get constant rate, basically eliminating the lambda. And afterwards, as David has talked about, that the symmetric key research caught up. They managed to have very efficient, concretely efficient Garbling for arithmetic things, but still having this rate lambda. And more recently, that the Aarhus team are the first one who managed to do rate 1 for integer arithmetic Garbling. And following their work, that with Yuval and Hanjun, that we did rate 0 Garbling, but weak Garbling for only simple programs or for privacy-free Garbling. You're asking a very good question that I wanted to hide under the rack, which is yes. So in this case, I give you the length of the wire, the bit length of the wire value for free. Yeah. Okay. So the more recently, the very exciting 3 works that Xiao just talked about, achieving rate 1 and. I will talk about this work, and then also the Aarhus team had the concurrent result under different assumptions. Our work and the Aarhus team's result, we work with groups, which was not known before. And also our result extends to arithmetic Garbling for ZP, and this rate hits no matter how large P is. Okay. Okay, furthermore, if you are wondering about whether we can go below rate 1, we can. For layered circuits, we can get some tiny advantage below rate 1. And there's also work which showed that using linear homomorphic encryption, you can go a bit below lambda, rate lambda, that we won't talk about. All right, so what I will focus today is to tell you about how we can look at succinct Garbling in a way that connects with homomorphic secret sharing, and specifically using this new tool called algebraic homomorphic MAC, which we believe is very useful on its own.
Do you have permission to use the H mark?
That was a thing committed by prior people. Okay, but I feel you, and I'm sorry.
We have an A to distinguish.
Okay, all right, so how did the Garbling get connected with homomorphic secret sharing? Well, that is curious. So basically in Garbling, as we have seen, that we can see the labels of the wire values as this kind of s times x plus k. This is basically free XOR inspired, except we now generalize it to general rings. We can think about what kind of ring. You can think about Z2, you can think about ZP, you can think about polynomial rings. And then the values are typically just a scalar. The wire values is a scalar over the ring. And the offset, the key S and the k are vectors in the ring. And it's typically convenient to think about that the secret S ends with a 1. Okay? So what does Garbling do? Garbling basically says, I want to start with this kind of label and allow the evaluator to get the same kind of label for the output. And with the help of the garbler, by sending to it some garbble circuit, right? And additionally, we should think about the garbler's algorithm is basically coming up with this auxiliary information to help the evaluator. And also, in the end, the garbler should obtain the KC that is blinding the output. And this means that if the garbler wants to just let the evaluator recover the output, it can just give out the last coordinate of KC. If it wants to allow the evaluator to authenticate the output, then it can give out the entire KC. Okay. So written in this way really looks kind of like homomorphic secret sharing. Why? Because, sorry for this, guys. I thought I fixed it. Why? Because these two things is essentially a secret sharing of S times X. Let's call it an authenticated secret sharing. So essentially, we want the garbler evaluator to start with authenticated share of the input and evaluate authenticated share of the output. And it is allowed to send some auxiliary information. Well, isn't this very similar to HSS? In HSS, the two parties start with share of the input, and they obtain share of the output. In fact, typically in HSS protocol, the share of the input do contain an authenticated share of S times X, and they do evaluate, in the end, an authenticated share of the output S times Y, except that they also need to give Alice and Bob both encryption of the input X. Okay, so they look very similar, but with important distinction. 3 distinction. HSS has no communication. Garbling allows one-way communication, and that communication is the garbble circuit itself. HSS allows both parties' computation to depend on the input X. How? Because of that ciphertext of X that Alice also received. But in the garbling world, we want the garbler to not depend on X at all. Finally, in garbling, we want to handle all circuits, but HSS so far is restricted to low depth evaluation. So in order to get a garbler, we have to overcome these drawbacks. And the new tool that we overcome is using this algebraic homomorphic MAC, AHMAC. And what it says is that, well, basically, garbler Alice and Bob hold authenticated share of the input, and there's some public data that is very small and reusable. The new game in town is that Bob actually knows what the value is. In some sense, the Bob is able to compute the entire output on his own, except that it cares about getting the authentication. Okay? So this is basically a MAC for X turns itself into a MAC for Y by Bob doing local computation. And additionally, Alice is able to locally compute the corresponding KC that were allowed to open the output Y. Okay, so homomorphic MAC is an interesting primitive on its own, and it has the application of outsourced computation that you can simply send this MAC for X to a server, Bob, let it do the computation, and send back the output MAC, and the Alice is able to be certain that the computation is done correctly. And what we show is that using DDH over prime order group or Pallier group or ring LWE, we can obtain arithmetic HMAC for circuits. And if you allow circular variants of the assumption, then we can handle arbitrary depth circuits. And this was prior only known using lattice or I/O or sub-exponential assumption over the groups. Okay. And additionally, the HMAC, AHMAC itself is quite concretely efficient. Okay. And using this tool, we can already expand the group-based cryptography, we managed to show that there are consequences for a couple primitives that we didn't know before that in fact achieve exponential improvement when using groups. I won't go into them very deeply, but let's see that the most important technique perhaps I can show you today perhaps is how do we construct this arithmetic, not arithmetic, algebraic HMAC. And we already see that those shares themselves are very additive homomorphic. So all what we need to do is basically to handle multiplication. I want the two parties to start with these shares. Additionally, the one party Bob knows the value. And at the end of some operation, local operation, that Bob ends up with the label for x multiplied with y together with xy, the value. All right, so quite easy and simple in hindsight. So we have, the evaluator has these two labels, Lx, Ly. Well, what about they just multiply them? If you do the grade school multiplication, you will end up with this expansion, right? Because you'll have s squared times xy, s multiplied with x and ky, and s multiplied with y and kx. Okay. This is not so good. Why? Because what we are afraid of are cross terms. There's no communication. Only Alice knows x and y, but only Alice knows kx and ky. Bob knows x and y. But how are they going to manage to compute those cross terms without communication? And this is further problematic because there's a lot of case, right? Even if maybe I have a little bit of communication, but there's really a lot of case. That's too much to communicate. So if we're smarter, in particular Beaver is smarter, came up with a different way of doing multiplication, which is that replace k with L, replace with the L that Bob already knows. Once we do this, we're going to see that their s squared times xy appears 2 more times, and this flips into a minus. Why is this way of multiplying really nice? There are still cross terms, but as you see that the cross terms only involve a single value, which is s. When there's only a single value unknown that is s, well, we can give out the encryption of it, right? So in the group world, if I can give out g to the s squared and g to the s, well, then suddenly I can evaluate this equation. What does evaluating this equation in the exponent mean? It means that one can form a multiplicative share of 0. Okay? This is basically the key ideas. Okay? To drive it home, we have this key equation written on top. What we're going to publish is g to the s squared and g to the s as promised, but also with additional plus s in the first ciphertext. What do we do? Well, the evaluator is going to raise xy. It wants to multiply xy with s squared, and wants to multiply this term with s, and multiply basically Lx, Ly with 1. Using this identity, we know that this evaluates to s times xy. This is why we added this additional term. So we have s times xy in the end, with what is being left over, which is g to the kx, ky. And g to the kx, ky is something that the Garbler can evaluate on its own. So they end up with a multiplicative share of s times xy. How do we go back to an additive share? Distributed discrete log. Okay. So as is, this already gives us an AHMAC. This relies on what we call circular power DDH in order for this to be safe to give out these encodings. If we're willing to pay order D amount of communication, we can simplify the assumption to the standard DDH. Okay. We also have a lattice instantiation, which would become closer to Shell's protocol, but I won't go into them. Idea is fairly similar to the group. Okay. How much time do I have?
5
5 minutes. I don't know how much I can go. Yeah, OK. We have, so let me now wrap it up. So we can sort of see that AH map, by wrap it up, I just meant wrap it up this view on AH map. We can view AH map globally as evaluating authenticity share of X with X to Bob to authenticity share of Y with Y to Bob. And particularly, it would be useful to remember that Bob's share resembles gobble circuit labels. So back to garbling. How can I use this tool in garbling? We can actually use it in 3 different ways. It can give me fully succinct partial garbling without privacy guarantee, very basically in 1 step. We can also get fully succinct garbling for some simple programs. And finally, we can get partially succinct garbling for all circuits by sending 1 bit per gate. Well, how does it connect to partial garbling? And what is partial garbling? Partial garbling basically says I have a computation where a large part of it is completely public, which I'm evaluating some public circuit on some public input. And its output is being fed into some private computation with some private input Y. In this case, there are many nice examples of such circuits. For example, conditional disclosure of secrets, or another classical one, which is I perform a large public homomorphic evaluation of FHE ciphertext, followed by private decryption. Okay? In all these computations, we can see the public part is actually really large. The private part is quite small. And when we gobble such a computation, we would like to not pay for the cost of the entire computation. And thanks to the fact that public input is public, it is known to both the evaluator, and we don't have to hide it. Therefore, we can hope that the entire gobble circuit only grows with the private part of the computation. And this can basically be done off the bat using AHMAC. How so? Well, basically, we can use AHMAC to evaluate the public computation, right? They can start with the authentic share for X and X known to the evaluator to authenticate share of the public computation output with Bob knowing the output of the public computation. And at this point, they just basically want to do the final private evaluation with private input Y. How do we do that? Well, basically, standard gobble circuit can work. Thanks to the fact that Bob's share is essentially a gobble circuit label. So if Bob additionally obtains label for the private input Y, and the gobbler give Bob a Yells gobble circuit, a classical Yells gobble circuit of the private circuit, they will be able to get the label for the output. Okay. So overall, the whole cost is dominated by the private circuit. Well, this is partial gobbling. How does that give me, how can I remove this partial part? Well, if I want restore privacy, the best way, one way I can do that is basically use homomorphic encryption, right? To compute an input with a private, to compute a function with a private input X, it's equivalent to first homomorphically evaluate on the ciphertext of X, and then perform a private decryption. Okay? So this fits exactly into partial gobbling framework. So what I can do is I can do the homomorphic evaluation using the AHMAC, and only perform the private decryption using the classical gobble circuit. Okay? And this will give me succinct, fully private gobbling, albeit that I am using homomorphic encryption, right? Is it interesting? If I want to not use the full-blown homomorphic encryption, it turns out that using much weaker, different assumptions, we can get homomorphic encryption for restricted type of programs. And therefore, our framework immediately gives you succinct, fully succinct gobbling for all these simple programs. Okay. But still, this is really relying on relying on the fact that we're dealing with simple programs, what if our goal is really to handle all possible circuits? It seems still very difficult to do without resorting to using the all-powerful homomorphic encryption. And this we can actually do by rethinking it in a different way. Suppose I'm only using a very weak homomorphic encryption, which can only handle very simple programs. One way that I can handle a complex circuit is to cut it into many different pieces, right? And I hope that for each of the pieces, we can actually start with do the evaluation homomorphically using AHMAC. Then, in order to do the next piece evaluation, I don't want to decrypt this homomorphic encryption, but rather I would like to re-encrypt it, because we have exhausted all its homomorphism. So I would like to move from an output ciphertext back to a fresh ciphertext. But this is not feasible by publishing a Yells-Garbling circuit for each re-encryption. We can try, it will work, except it will be gigantic, right? Instead, the key idea is that we're going to use homomorphic secret sharing instead to do the private re-encryption. And what's also nice about this paradigm is that we can actually work with homomorphic encryption that have non-compact ciphertext, because no one ever communicates these ciphertexts. And since my time is kind of up, okay, maybe 2 more slides. Okay, why, to just give you a very quick idea, why homomorphic secret sharing can help us to do re-encryption. The ability of homomorphic secret sharing is it allows me to start with share of X to share of Y with the help of an encryption of X. But if you extend it slightly, we can actually add computation with another value, A, that is not encrypted. Except that the computation on A is very simple. I can only evaluate linear function on A. Okay. So this is what HSS off the bat can give me. And it actually guarantees the privacy of all the values. So suppose my re-encryption is extremely simple. It's simply take my ciphertext, multiply with some function of the secret key. That's how re-encryption works. Well, this fits right into HSS, right? Because I can just like, yeah, the ciphertext is going to be my A, and X is my secret key. And HSS takes responsibility of computing some complicated function of the secret. And it can also do something slightly more complex, basically is to add an additional sum on top of this. So essentially, I need a homomorphic encryption where the re-encryption is a linear function on the ciphertext. And it turns out that one-time pad is such a function, is such an encryption scheme. I won't go into why one-time pad is such an encryption scheme, but basically this. Then we can use HSS to do re-encryption of the one-time pad. And where does the communication come from? Is that at the end of the evaluation, I end up with a fresh one-time pad encryption of the value. But I still need to make sure that the Bob will actually know this ciphertext in order to continue evaluation using AHMAC. And that requires us to communicate the blinder factor on this one-time pad ciphertext, and that costs 1 bit per wire. Okay, so that's what I all want to tell you. So in between is a great space. We've already made some advances using linear homomorphic encryption and HSS. But still, the 2 questions remains widely open. And the even bigger question is, with this broader design space, what more can we bring to Garbling? Thank you.
Right. I think if you have questions for Rachel, I encourage you to bother her offline, because that concludes our scientific program for the day. But we do have what am I trying to say, Tal? Reception. We do have a small reception outside that we would love to see you at. and then we'll see you again tomorrow morning. So thank you all.